All right, so if we recap some of these bonds that we've been talking about, one thing that we mentioned before was distinguishing these terms here: dissociation, hydration, and ionization. Right? Dissociation is the splitting of an ionic compound into ions. The positive ion is called cations, the negative ion anions. Then water does something to it. What? Water surrounds those cations and anions. That's called hydration. When a chemical change occurs, that goes further to become ionization. This is very similar to dissociation, except this is a chemical change, so something new is formed. Water hydrates in both cases. It surrounds the ions, and like we said, we've got a polar molecule water. This is our Mickey Mouse here, positive end, negative end. We've talked about a lot of bonds, the intramolecular bonds. We mentioned ionic compounds. What is an ionic compound? An ionic compound transfers the valence electron. Okay. The END, the electronegativity difference, is above 1.7. Then we have the covalent bonds, sharing valence electrons, and the electronegativity is below 1.7. Okay. Covalent bonds can be divided into, right, nonpolar bond. What's the only way a nonpolar bond can exist?
Same atom.
The same atom. So there are how many of those?
7.
7. They're Professor
Hofbrinkel
elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Okay. So since it's the same, the electronegativity is equal to 0. Okay. That's a nonpolar bond. Then you have polar bonds, okay, where the electron distribution in that molecule is uneven, so it kind of makes what we call a dipole, right? And a specific example of this is a coordinate covalent bond, where what happens here? In a coordinate covalent bond, one of the atoms actually donates both of the electrons to the bond. Okay? Very common in what are called polyatomic ions. We'll talk about that next unit. Intermolecular bonds. We start here with LDF, London Dispersion Force. Okay, what is that? Sabrina? London Dispersion Force is a dipole to dipole temporary attraction. Okay, so you draw like a plus minus. It's where the electrons are, again, they're moving constantly. So what if they're on the one side of the molecule while they're moving? That side becomes relatively negative, the other side positive. And if another molecule comes up to it, right there's your attraction. Now, what was evidence showing that these bonds exist? One of the evidences, we looked at the halogen family. Remember? What's the state of fluorine and chlorine?
Oh, yeah.
Gas. The state of bromine is a liquid. The state of iodine is a solid. So they're a family. You'd expect them all to be the same state, very similar property. When we look at a gas, liquid, and solid, we're looking at the molecules. Gases go very fast. The molecules are random. They're crazy. Liquid, they're much slower, but they're still moving. Gas, or a solid, we even say they're vibrational. What slows them down?
Attraction.
Some kind of attraction. So we're saying, since it's in the same family, we'll call it the London Dispersion Force. Okay. Hydrogen bonds, there's all kinds of stuff going on because of a hydrogen bond. So let's name some of those things. Because of hydrogen bonds, we do look at this. Water, which has the hydrogen bonds, dissociates things very easily. And it hydrates, so that was one big thing. How about water's boiling point? It's almost 200 degrees higher than you'd expect because of hydrogen bonding. So that's the second thing. What else? What does water do that no other substance that we're aware of does? It is less dense as a solid, so it floats. That's important. And then we did a demonstration where we, burned a towel and the towel didn't burn up.
Specific heat.
High specific heat. The water absorbed the flame that the alcohol was giving off. It absorbed it. Pretty cool. And then one last one. It had cohesion, adhesion.
and capillary
Yeah,
action.
it's called surface tension. It's all, and capillary action. It's all related to hydrogen bonds. Okay? Van der Waals forces. They're actually the same thing as London dispersion forces, but two different places discovered it. Won't give the other one credit. They want to take credit. What did we use here for evidence? We used the same evidence here as London dispersion force when it came to the halogens in the column. The gas is fluorine and chlorine. Bromine's a liquid, iodine's a solid. So that same thing, both take credit for. But this one, we mentioned another kind of attraction, and that was related to the noble gases. You remember that? The inert gases like helium and neon and xenon and all those. How do they stay together? How do you collect them? There has to be some kind of attraction. And
Wasn't it
again,
like temporary?
yeah, it's a temporary dipole. The electrons shift, they move. So when they're both on the same side, or all on the same side, they're more negative than this is relatively positive. So that's a van der Waals force. Molecular ion attraction, a polar molecule, the polar bond, is attracted to maybe an ionic compound. And again, water did that where it hydrates, surrounds it. That's that kind of attraction. Network solids, what are those? What's the other name for it again? Macromolecules. So they're very large. Say. Okay. What are some examples of network solids? Diamond, graphite,
Silicon dioxide.
silicon dioxide makes up the earth, and it's used in all of our lab equipment, the glassware.
Phosphorus.
What?
Phosphorus.
Phosphorus. When two things like diamond and graphite, they're both made of carbon. What do we call those? Allotropes, right? That means they're the same basic stuff, yet they're completely different compound. Or molecule, sorry, not a compound. They're a completely different molecule. All right? What are the characteristics of network solid? Huge, very high melting point,
Ductile.
hard,
Insoluble.
they're not soluble,
Hard crystals,
Yeah.
insoluble.
hard crystals.
Poor conductors.
Yeah. Poor conductors, so again, that's in there. And the last thing was the metallic bonding. How would you describe a metallic bond? See, what you expect, like in an ionic bond, you have, let's say, two ions, sodium and chlorine together. And sodium gives up its electron to chlorine, right? It's like you can designate where that electron goes. When we're talking about a metallic bond, remember I used the pond or the lake example? You got buoys in a lake, and those buoys represent the kernel of the atom. So the kernel would be the nucleus and all the electrons beside the valence. What would the water represent? The valence. And the valence means those electrons, they don't have to be designated to any particular metal atom. They can go anywhere, they can move.
Oh yeah, they move between.
So what are the properties of metals? Malleable, you can shape them, bend them all over the place.
Ductile.
They're ductile, you can make them into wires.
Good conductors.
Good conductors of electricity and
Luster.
heat.
Reflect.
They reflect.
Shine.
And there's one more, right?
Hard.
They're very strong, they're very hard. Now, where does it get all those properties? If you think about it, the theory, the explanation is called a metallic bond. The electrons, instead of being designated to a particular atom,
They're everywhere.
they're just like the pond water and around the buoys. It can move anywhere. So it's only the valence we're talking about. So it gives flexibility. To give reflective properties or luster, that's the electrons that actually scintillate off the surface. You look at a metal, you can see them shining, right? Same thing, to make it ductile or to make it malleable where there's movement, there's flexibility. It's those valence electrons can move a little bit, and yet they're still super hard.